Our story begins in the midst of the 17th century, which is considered to have been a time of great scientific curiosity, with one of the topics of interest at that time being the properties of empty space. Just a bit over 5 years earlier, the creation of the vacuum was achieved by using mercury, which was able to produce only a very small vacuum within a localized contained area, which quite limited its experimental usefulness. Up to this point in time, the real challenge was to create a substantially large enough vacuum that could also be maintained for long periods of time. However, a man called Otto thought that he might be able to provide a solution. And indeed, he was the first one to produce and build an air pump, which allowed for maintained vacuums to be created within any container that could withstand the difference in pressure. This allowed for numerous experiments to be conducted, some being stranger than others. The focus of this story, however, is the bell-in vacuum experiment, a truly creative name for an experiment where you place a bell in a container, remove all the air from said container, and then ring the bell. However, the validity of those results were quickly under question, as there were variations in the intensity of the volume that was being generated by the bell, sometimes with the sound being louder and others quieter. This led to a single conclusion. Since the only possible variable in the experiment was the amount of air present within the container, it meant that the supposed vacuum that had been created was shit, which in turn meant that the air pump, at least to the degree of accuracy needed for this experiment, was also shit. A few more years had to pass when a physicist named Robert Boyle noticed that problem and thought that he could do a better job at it. And so he went off and 2 years later returned with a new and improved version. When the experiment was conducted again, this time around there was no variation in the sound. In fact, when the bell was rung, there was no sound at all. This might not sound like a big deal to us nowadays, but back then this innocent experiment had created some quite scary implications of its own. Up to this point, scientists knew that all waves required a medium to travel through. Water waves required water, seismic waves required the earth, and sound waves require air, which indeed the experiment showed to be true, since when the bell was inside of the vacuum where there is no air, no sound was generated when it was rung. However, even though you couldn't hear the bell, you could still see it. This implied that light could travel through a vacuum and therefore did not require a medium, going against everything that was known at the time. The fact that light appeared to be so fundamentally different than any other known wave didn't sit very well with many, and especially with Boyle, the one who indirectly led to the discovery being made in the first place. But Boyle, just like any good scientist, didn't give up. He went back to his house, made some shit up, and threw a bunch of ideas at the wall to see what sticks. At the end, he was left with one idea, that of luminiferous ether. The ether was proposed as a medium that light used to travel through, but for understanding how it functions, it is important to know some of its required parameters. It is invisible, which makes sense. It is weightless, which, okay, I can understand that. It is undetectable, which seems a bit convenient, and it has no effect on physical objects. Right, so all the things that would make it extremely difficult, if not impossible, to prove its very own existence. So it'll probably not come as a surprise that it took over 200 years before an experiment was devised to test the ether. Now, to be fair, there were some first-order experiments that took place within those 200 years, but not a single one was able to directly prove or disprove the hypothesis, and so we will not really worry about them. And so, the year is 1887, and two scientists named Albert Michelson and Edward Morley had just designed and built an experiment that would test the seemingly impossible idea of Robert Boyle, with one of them being very passionate to prove it correct. The experiment in question is the famous Michelson-Morley experiment, once again a very creative name, but to fully understand how it would work, there is one last parameter about the ether that I left out, the fact that it is everywhere. And by everywhere, I do mean the entire universe, the ether should exist in your room the same way that it exists in the solar system or our galaxy. Since it is the medium for light, then anything that the light touches, it does through the use of the ether. Taking that into account, we can see that as the Earth orbits around the Sun, it is constantly moving through the ether. The benefit of this is made clear when we change our perspective so that the Earth becomes the inertial frame of reference, making the ether appear to flow around the Earth like a wind. In order to understand the usefulness of this change in perspective, we can conduct a simple thought experiment. Let us imagine the current of a flowing river. Say that you want to swim in a 100-meter straight line and then 100 meters more back to the origin. Let us take two paths, separated by 90 degrees. Path A will have the first half of the journey go along the flow of the river, meaning that during the return trip back to the origin, you will have to swim against the flow of the river. Taking path B, you will be traveling perpendicular to the current in both halves. And so, in order to be traveling at a straight line, you will have to swim at an angle as to counteract the effects of the current. And so, the question becomes, which one of the paths would take the least amount of time to travel, or would both take the exact same amount of time? To solve this, we can plug in some arbitrary values for the constants, and just to make the maths as simple as possible, let us say that the river flows at a speed of 3 meters a second, and the swimming speed is 5 meters a second. For path A, in the first half the speeds combine to give us a total speed of 8 meters a second to travel the first 100 meters, which takes us 12.5 seconds. On the return trip, however, the current is against us, so the total swimming speed becomes 2 meters a second, meaning that it takes us 50 seconds to swim back to the origin, giving us a total time of the journey of 62.5 seconds. Taking path B means swimming at an angle, resulting in a triangle with the hypotenuse being the swimming speed and the opposite being the speed of the river, making the adjacent 4 meters a second, which is the swimming speed in respect to the straight line. This means that the time taken to swim 100 meters is 25 seconds. And since in the return back to the origin, the same triangle forms just flipped on its x-axis, we know that the resultant speed will also be 4, and so another 25 seconds, bringing the total to 50 seconds. Michelson and Morley had a similar idea, where we can replace the current of the river with the apparent flow of the ether as the Earth orbits around the Sun, and instead of a person swimming, it is a light beam traveling through the ether. If we make the experiment, have two beams that are separated by 90 degrees, start at an origin and travel a set distance to their respective mirror, and then are reflected back to the origin, we should be seeing a similar result as we did in the thought experiment, meaning that one of the beams should take longer to arrive than the other. The challenge now translates to our ability to measure the difference in arrival time of the light beams. And due to the extremely high speed of light and the fact that the size of the experiment was that of a desk, you might be thinking that directly measuring the arrival times of the beams would not be possible. And you'd be right. With that in mind, there is an interesting solution that emerges, which comes from the fact that light waves can interfere. This means that if the two beams are in phase, then they constructively interfere, creating a brighter middle peak than a single light beam. But if they are out of phase, then when they are combined, the middle peak will be dimmer due to them destructively interfering. The idea for the setup of the experiment was quite simple. By taking a uniform beam of light and shining it at a half-transparent mirror in order to split the beams into two identical ones that are 90 degrees apart and start off from the beam splitter at the same time. Then the two beams travel to their respective mirror, with both placed at an equal distance from the origin, and as the beams are reflected back, they are recombined and once again as one beam go to a screen. If the light beams arrived at the same time, that would mean that when they were recombined, they were in phase and will create a bright middle spot. However, if the ether is present, then one of the light beams would be a bit slower to reach the origin than the other after it was reflected, causing the beam to arrive at a different time, therefore be out of phase and destructively interfere, causing a dimmer middle. And after 200 years of waiting, at long last, the final result of the experiment is... it seems that both beams arrived at the same time, which means that the ether does not exist, which must have been a revelation to them. But here's a twist. A similar version of the experiment had actually already been conducted 6 years prior, and by none other than Michelson himself. But obviously the man who walked into this experiment hoping to be proving the existence of the ether wasn't too pleased with those results, and so he just didn't publish them, at least not for a long time after the fact. Michelson said that the results were inconclusive and that they needed to try using different distances from the mirrors, more accurate measuring equipment, different orientations, all things that ended up not having any effect on the final result, with the beams always arriving at the same time. And for those 6 years, he simply persisted in doing the same thing over and over again, expecting a different outcome. Until eventually, Michelson conceded defeat. With Morley being there to verify the accuracy of the experiment, he agreed to have their findings published, disproving the existence of the ether once and for all. However, this leaves us with the same problem as before, but now it's amplified, because now we know that light cannot possibly have a medium, and that mystery would remain until... Luckily though, as all of that was going on, a Scottish mathematician named James Clerk Maxwell had published a paper for a complete theory of electromagnetism in 1865. This consisted of 4 equations, one of which described the speed of electromagnetic waves through different mediums, by using the permittivity and permeability of those mediums. And since electromagnetic waves are self-propagating, this also means that they can propagate through a vacuum, meaning that a constant speed can be calculated using that equation by substituting the values for free space. Up to this point, Rome's measurements of the speed of light was one of the best estimates. He achieved this by using the moons of Jupiter, with the value being 226,663 kilometers per second, which was very similar to the answer that Maxwell was getting from his equation. Therefore, he deduced a hypothesis that light must be an electromagnetic wave, solving the issue of its ability to travel through a vacuum, and with the disproof of the ether, all seemed to be pointing towards that possibility. And just a year after the Michelson-Morley experiment, a physicist named Heinrich Hertz proved the existence of electromagnetic waves by being able to produce radio waves using a spark gap transmitter. This experimentally proved that light was indeed an electromagnetic wave and was able to travel through a vacuum without the use of a medium, showing that Maxwell's equations were correct. That last point, however, had created a new problem in itself. Like we talked about prior, the speed of light had been estimated by Romer in 1676, showing that it was a large but finite speed instead of light being instantaneous as it was believed at that time. And even though the actual value was larger than Romer's estimate, Maxwell's equation still made a crucial distinction, which was that it was a constant based on the very nature of the vacuum itself, meaning that this was the highest possible speed that light could achieve, lower when passing through a medium, but mathematically impossible to ever be higher. And what everyone wanted to know was why. Skipping a few decades forwards from 1888, we step into 1905, where the beginning of that answer is being formed. As in Switzerland, a young man named Albert published 4 papers in that one year that changed physics forever. Besides proving the existence of atoms, linking mass and energy as two sides of the same coin, and putting in place the initial blocks that would go on to make up quantum mechanics, even though he personally disagreed with the concept, the most important paper, at least for this story, was that of special relativity. As this paper, and with the added DLC just a few years later, was able to rewrite the theory of gravity. Now, to answer the question as to how a new theory of gravity could possibly resolve the question about light having the highest possible constant speed, we need to tackle some of the rules that relativity set. Mainly that the speed of light is not dependent on the motion of the source or of the observer, meaning that in a vacuum, the speed of light would be a constant no matter the relative speed of the observer. But this is linked to the most well-known aspect of Einstein's relativity, which is the concept of spacetime, a fabric that explains the changes in both space and time due to the presence of different objects, and by making light a function of that spacetime, we can use the concept of least resistance. Which means that the changes in spacetime result in light having to always take the shortest possible path between 2 points. Due to the maximum speed that light can reach, it results in space and time dilations being possible. The latter meaning that different observers can experience the passage of time at different rates, meaning that for different observers the exact same event can take place at different times. In 1938, the Ives Stilwell experiment for the first time proved the existence of the phenomenon of time dilation by measuring the additional shift in the frequency of emitted light from high-speed particles. The phenomenon of time dilation has been confirmed many times since, and it's most well known due to the need of taking it into consideration for GPS to function correctly. And with that confirmation, it proves that light is a fundamental part of spacetime itself. However, for many this was mostly seen as a cherry on top, as the theory of relativity had already been experimentally proven up to that point, most famously with the very first experiment, which observed the light of a star bend around the Sun during a total solar eclipse, just like the spacetime around it, and have it appear at a place different than it actually was in the sky. Thus, the results pushed the theory of relativity to enormous amounts of fame, mainly due to the fact that Newtonian gravity was thought to have been one of, if not the most well understood and complete theory of that time, and it was just rewritten. In the following years, decades and century since their publication, there have been countless resultant predictions from the mathematics of special and general relativity, which have been proven correct time and time again, such as explaining the previous unexplainable orbit of Mercury and predicting the beautiful gravitational lensing. It also predicted the existence of black holes, which were first discovered in 1971. More recently, in 2018, there was this complete video of seeing stars as they orbit around a black hole. And lastly, in just 2019, there was the very first image of one. There have been a number of outlandish predictions, many to be proven true, and some that are yet to be proven. But one prediction that for the longest time was thought to have been impossible to ever be proven is that of gravitational waves. The simplest way of describing them is as ripples in spacetime caused by massive objects moving at extremely high velocities. The most common example being that of two orbiting black holes. Even though the processes that generate gravitational waves are greatly energetic, those events take place so far away from Earth that by the time those gravitational waves reach us, they are at a scale of 10 to the minus 20 meters, 10 billion times smaller than an atom, which is exactly why we as humans cannot feel those variations in spacetime. And for the longest time it was thought that even the most sensitive detectors that could possibly be built wouldn't be able to detect such changes without being massively hindered by noise interference. However, a group of researchers thought that it could be possible given a large enough scale. After 8 years, in 2002, this was the detector that they had built.
Hey, I've seen this one. This is a classic. What do you mean you've seen this? It's brand new.
Hopefully, you can recognize the similarities to the setup of the Michelson-Morley experiment, the most notable difference being that one is the size of a desk and the other one has arms that are 4 kilometers in length. And instead of the ether, this detector was trying to measure changes in spacetime, and in the scale that would allow for the detection of gravitational waves. Nonetheless, it uses the same idea of having light arrive at different times. In addition to the scale of the experiment, their best attempts at eliminating noise by having light beams travel through a vacuum and also having the mirrors being suspended would theoretically allow for detecting the smallest of variations at arrival times, as it hoped to measure if one beam had traveled 1/20 billionth of an atom diameter longer than the other. And in 2016, they published a paper showing that the very first detection of gravitational waves had taken place. Every scientific magazine for the next few months had its majority dedicated to this discovery, as it was for the very first time that it was possible to get information from billions of light years away without using light. Observations continued years later and were further confirmed by the addition of optical observations of these high-energy events when they involved at least one neutron star, therefore solidifying the existence of gravitational waves and managing to prove yet another prediction of general relativity correct. Now, I'd like to take some time to just step back and look at the story that this discovery has gone through. Long ago, it was discovered that a wave did not behave like any other known wave, and someone came up with an extremely difficult to prove hypothesis in order to explain it. For 200 years, there was no answer to it, until someone that really wanted to prove it right built an experiment and achieved the exact opposite of what he wanted. Then almost 120 years later, the very same concept from that experiment is used this time to indeed prove correct the theory that finally had explained why light behaved as it did. I believe that there is a certain beauty to this story. Unfortunately, this story is not told as often as it should be and is part of a long list of such stories. I understand that it can be seen as too long for people that write articles in magazines or by people that give talks on the subject, but due to just skipping forwards and only talking about the discovery itself, we miss the most important element that science has to offer us. There are definitely hundreds and quite possibly thousands of articles written on gravitational waves, and how they've proved Einstein right once again, and how they're the discovery of the century. But discovery is not the most interesting or important part when it comes to science. It is about how that discovery got made. Why did we end up with the experiments and theories that we did? Why were the results interpreted the way that they were? Newton famously said, "If I have seen further, it is by standing on the shoulder of giants." And that was Newton, saying that back then. Think about how much more we know about physics nowadays, how much further we can see. And if he spoke of giants, we should be speaking of titans. There is a certain depth created by all of those different layers coming together to produce the knowledge that we have today, through people being wrong, through people making experiments, through people trying to interpret the results in a coherent solution. And it is truly unfortunate that this depth is being swept away from us, for our convenience, mind you, resulting in the extinguishment of our own curiosity. Now, I don't blame people for not being interested, because they are not really the ones to blame. At the end of the day, if you could supposedly understand an entire branch of physics in just a single paragraph, well then, what is really the point in wasting your time reading an entire book on that very same branch?